We have observed 7 experiments over the past 50 years that give valuable insight on exon skipping technology in the treatment of Duchenne muscular dystrophy, also known as DMD. The works we have identified begin with Bullfield in 1978 and 84, to Koenig in 87, Sicinski in 89, Dunkley in 95, Sepsky in 2003, and Mendel in 2013. I'd like to note the works of Sicinski and Gebsky in particular, as I see some rather interesting steps being made in these particular experiments. With this in mind, it is still important to note that all these studies are respectable and significant in their contribution to the treatment of DMD. Bullfield had initially discovered a mouse with different enzyme levels. This then developed into discovering an X-linked trait where its histology is similar to that of DMD patients. These mice would be deemed as MDX mice and would be a focal point in the development of exon skipping technology. As we ultimately, undoubtedly, superior humans don't test on ourselves first, but rather animals. The work of Bullfield then funneled to Koenig. Koenig and colleagues had worked to identify the types of mutations occurring in patients. In particular, they identified deletions in dystrophin. They began to establish the RNA sequence in which this occurred and then used probes or northern blot analysis against patient DNA to identify deletions that had occurred. This work could only show large gaps in the sequence of the DNA, though, not frameshift mutations. Despite this, it was a positive step in slowly identifying the source of disruption. Sicinski and colleagues' work then focused on pinning where the mutation occurred. Sicinski initially hypothesized that the mutation type and location in the mouse dystrophin sequence can be resolved by southern blot hybridization probes spanning the cDNA length. To test this, they collected the RNA from the cell, converting it to cDNA so the exon sequence is stabilized. When stabilized, they used enzymes to break the sequence at specific sites and placed probes for comparisons to be made. The probes would allow the group to identify whether certain segments were present or, in other words, complemented. Southern blot analysis did not show where the mutation was, though. The mouses, in fact, still had the whole transcript of the dystrophin gene. The group then moved onto DNA sequencing to identify point mutations. The way the DNA sequencing was conducted was through cloning of complementary DNA from mouse dystrophin. The sequence was then used in the polymerase chain reaction to amplify normal and MDX dystrophin transcripts in the area of the MDX mutation. The group would use AGCT terminators to read out these sequences, and this would ultimately result in identifying point mutations in the MDX mouse. They ended up discovering that just a single nucleotide had disrupted translation. This finding would provide implications for finally understanding DMD. Although Sicinski et al. Found multiple types of mutations, they found the majority to be point mutations. This data had inspired Dunkley and colleagues to then identify whether or not the body can skip over that single point mutation. As the body normally moves from exon to exon in transcription, Dunkley and colleagues wanted to figure out how they could avoid the premature stop. Through testing whether a nucleotide sequence can be modified for transmission across the cell membrane, Dunkley had discovered that antisense oligonucleotide and PEI would lead to the formation of dystrophin on occasion. Soon after this discovery, Gebsky focused on finding the most effective doses of these AOs. Gebsky and colleagues hypothesized that splicing can be changed in a living organism when there is a paired delivery, also known as duplex, of a molecular complex and the RNA complement code. To test this, they created a molecular complex with morpholino and a leash. They then put this in a dish with cells with different concentrations of the RNA code and then measured these leashes for a 10-day period. The results demonstrated that with the lesser the dose, there's a lesser chance of making anything more than the original dystrophin. The higher dosages would input a greater influence on the transcript and cause the exon 23 skipping to occur. In particular, 300 nanometer doses would stay persistent in exon 23 skipping after 10 days, whereas 100 nanometer doses would fade away between day 4 and 7. The consensus appeared to be predicted, suggesting that the higher dosages of morpholino AO would be more effective in modifying transcript. To benefit from these findings, the question of how often doses should be administered to patients must have been asked. Mendel's study did so, experimenting with different dosages of eteplirsen and how patients would respond to treatment after 12, 24, and 48 weeks. The data from the study suggested that there's potential for eteplirsen to be used as a safe and effective therapy for DMD. Mendel's study really encapsulates the work of all these scientists and represents how close we are getting to the end goal. The experiments have fortunately funneled and become more and more fine-tuned in finding efficient treatment. Although DMD is a rather disheartening disease to hear about, it is important for us to remain hopeful and continue to strive to the end result we all want. By observing the history of research, I firmly believe we are heading down the right path.